All right, and next we have one of our other fearless co-organizers of this mini symposium, Ray Yang, who, if I remember correctly, is going to talk to us about FreeBird, and I don't remember the subtitle, an extensible toolbox for surface free energy calculation via nested sampling and beyond. All right, take it away, Ray.
Thank you very much. Today I'll give you a quick overview of the package we're building at the Wechsler Group at Washington University in St. Louis for simulating surface systems. If you're looking at this picture, you maybe get really confused and not sure what's actually happening. That's exactly the point. So we care about the surface at the so-called operando conditions, which conditions changes and the surface react, interact, and reconstruct all kind of complex things going on, and which is really hard to measure and also really hard to simulate. Fairly recently, we published this proof of concept work using nested sampling to study this coverage temperature phase diagram of a simple Lennard-Jones solid with 1 facet. So what we typically do is we sample microstate and we construct a partition function. From the partition function, we can calculate thermodynamic properties such as heat capacity. From there, we determine the phase boundaries and then we draw a phase diagram. As you can see here, for this simple, a free adsorbate condensing on top of a solid surface, we can have a gas as temperature lowered, and then they become disordered adsorbates, and as temperature further lowered, another phase transition happens, they become ordered adsorbates. And then we can also calculate other observables and other parameters. So we've done this with nested sampling, which is a fairly novel methodology, and we want to compare how it works with other sampling methods. And then we just thought about, why not just building a toolbox for doing all kinds of samplings, and also to kind of extend it in terms of what kind of system we can handle and what kind of energy evaluation scheme that we want to use. So basically, FreeBird is a really, really modular code. We had too many modules probably, but it's really intended to leave rooms for further extension and expansion. And we want to use calculators such like a simple pairwise interatomic potentials. We want to also use model Hamiltonians, and also we want to integrate that very popular, very powerful machine learned interatomic potentials. And currently we can handle atomic systems and in a continuum, so non-discretized system. But we also build a lattice, which I will show later. And here are kind of two examples of what the kind of type system you will encounter in FreeBird. Basically, we have a system that spans both horizontally and vertically. What I mean by that is you have your typical set of structs or types to dispatch and specialize your functions. And then we also have this type system to just embed and embed and embed. And it's like layer by layer. It's more like this nested system that kind of similar to the Smoky package. It's really allows us to do some really fast prototyping, experimenting with new methods, with still just a few core functions, to optimize and to retain the performance. Here I will quickly do some showcasing of what system that can be currently modeled with FreeBird. At this stage, many of the models are still kind of a proof of concept or coarse grain. It depends on how you perceive them. So here is a very, very simple system. It's just 6 particles in a cubic box interacting through a very simple Lennard-Jones potential. And in this figure, you see the plots of the heat capacity versus the temperature calculated from 3 different sampling methods. The blue one is the nested sampling, and the orange dots are the classical Metropolis Monte Carlo done at different temperatures, and also the green trace computed through the Wang-Landau sampling If you look at the code, the top one is kind of prepared for necessary sampling, which needs a set of configurations. And then we wrap the configuration, which is actually from the AtomsBase object into a atom worker, and we wrap the workers into a workers project. And then pass them into different sampling methods. And again, we intentionally try to keep everything wrapped in the struct, and then with a lot of default values just for the easy usage for users. And then here are the 3 lines to run 3 different samplings and then get different results. I had to mention that these 3 sampling schemes behave very differently. For this particular calculation, necessary sampling probably takes a minute. And for the MC, that each data point probably takes a few minutes. And for Wang-Landau, it's fairly challenging to run for this system, even with 6 particles. Basically, you're sampling like infinite energy levels, and it's kind of known to be challenging. But this will change once I get to the lattice part. Again, we can handle more than a single component. We can basically do as many components as you want. You just define the interactions between each component, and then again send them into this Lennard-Jones parameter struct. Very similar to the previous example, and we run the 3 different sampling schemes. And you can see that all of them agree fairly well. And then comes down to the surface system we actually really care. Again, that's the same example I showed from the second slide. We have 3 particles. First, I condense onto a surface. That's where you see the first very broad peak at higher temperature. And then there's a entropy-driven ordering transitions occurring at the lower temperature. Again, all 3 sampling methods agree fairly well. And here you can see that we actually read in a XYZ file instead of generating our own initial starting structures. So that's a functionality we have. Now, let's talk about lattice system. Embarrassingly, we built our own lattice system. We probably should just use the lattice utilities. But it's something that we want to keep it lightweight and just snappy. So we built a really, really simple parameterized type that the geometry and the number of components are the 2 parameters of this type. And also we build in some very nice visual, just that you can see directly from your repo. And this lattice is supposed to be interacting through a so-called classical Hamiltonian that in this example, it takes nth nearest neighbor interaction energies. This can be obviously generalized to do other models, icing models, and then just you define your interaction scheme. Here are the examples. Again, we run 3 sampling plus exact. What is exact? It's basically just enumerate all the possible configurations. From there, you will be able to construct your exact partition function. Same story, all sampling methods agree with each other and agree with the exact. And on the left, you have just a 2D, a single layer with 4 particles moving around. If you give it 2 more layers, it recovers this condensation behavior and then this ordering. So then we also confirm, this kind of universal physics of this adsorption process. All right, to quickly conclude, what we really want to build is a platform, and we leave a lot of room and space for further expansion and extension. And also we are able to confirm, let's say, the universal physics behind the surface phenomena. And it is actually a high-performance package, and we're able to run it on the NERSC supercomputers using a node, at least fairly efficiently. Lastly, I want to acknowledge the people who contributed to the group, and PI Dr. Wexler, and grad student Junchi, and undergrad student Douglas, and our serial collaborator Livia from Warwick. And I said for funding, JuliaMolSim for the support, because I asked a lot of questions there, and also demand features. And also we got quite a bit of computing resources to try on. And the code is available there on GitHub, and thank you for your attention.
All right, we are just about at time, but I know for a fact that Ray will be around, so if folks have questions, please catch him afterwards. And I think Jonathan is, oh, there, you're right there. Go ahead and come on and set up.